is Thomas Heaton, and Thomas is going to talk about internal forces from earthquakes on a Hyperloop pod.
Thanks. I'm an earthquake physicist, and I'm also a civil engineer, sort of a building physicist. And a couple of years ago, Pam Brogan came to Caltech and was trying to get interest and get Caltech students to sign up for a stint designing these things. I went to the talks, and it was interesting, I got to say, but 350 meters per second in a steel tube in an earthquake, what could go wrong with that? Well, I'm a pretty creative person. I could see a lot of issues right away. I mean, obviously, if you crossed a fault and it ruptured the tube, I mean, that's basically end of the game. And you want to do just the opposite. If you want to cross a fault, you probably want to do it at the surface. Although we do have some tubes that cross the Hollywood fault that runs through campus here, by the way. The subway up into the North Hollywood goes across the fault, and they built a big galley in the area where it crosses so that if there's slippage, they weren't thinking they'd save anybody, but it'd be faster to repair it afterwards because they wouldn't have to retunnel it. But I'll show you that even without the fault crossing problem, there's some very unique things that show up when you're traveling at very high speeds in a tube that's deforming in an earthquake. And you can't avoid having deformation of the tube in the earthquake. I mean, it's what an earthquake's all about. Waves are deformations that travel through a system. And probably the biggest problem will be making sure that if you got a tube that's suspended between different pylons to basically brace it, it will vibrate laterally. And when it vibrates laterally, if you're moving 350 meters per second, you're going to get some pretty big accelerations. These can probably be mitigated, but I have a scheme that might work. So this is just to remind you what these things look like. This is this is the Landers fault in 1991. This is a magnitude 7.1 earthquake. It was a little bit of a surprise to us out in the middle of the desert, and about 4.5 meters of offset here. You can see these Jeep tracks, and this is a lateral horizontal motion. There's some compression depending on what angle you cross the fault at. This was on a fault that was previously unrecognized. Oops. And going the wrong way here. Here's an example of an extensional fault. This was in 1954 in Nevada, and the ground is basically being extended, and the right-hand side is dropped vertically down by about 2.5, 3 meters. This was pretty poor engineering on his part to put his outhouse on the other side of the fault. I mean, it seems to be pretty depressed about that. This is from the 2001 Chi-Chi earthquake in Taiwan, magnitude 7.7. And in this case, it was just the opposite of the last one, where there's compression of the ground here of about 8 meters. And basically the left-hand side is thrust out over the right-hand side. And again, this would have been a very difficult fault to anticipate that was what was going to happen there. But it's at the base of the mountain, so you know these things happen. Here's a really interesting case from 2002, the Denali earthquake that runs through the middle of Alaska. It's a big strike-slip earthquake, very much like the San Andreas Fault. In this case, it started here to the left with about 5 meters, and then got up to about 6 meters, and ultimately there's a big long stretch of about 12 meters of slip along this part of the fault. What's interesting about this is that the Trans-Alaska oil pipeline crossed this fault right in here where it's about 7 meters. And the pipeline, they recognized that they were going to cross an active strike slip fault, so they designed it to accommodate both shearing and compression due to the Denali fault. Again, they'd had 6 meters of slip, and they were kind of lucky. Everything worked, but if it had been over here, it wouldn't have worked because the slip was twice as big over there, 12 meters. Most of the pipeline is above ground. There's some subterranean parts, and it's been built on these bents so it can move horizontally. Thermal expansion and contraction is a big thing on this pipeline. And if you look at it, they put in all these kind of S shapes so it could, when it expanded, it would bend a little bit. And so this is what the pipeline looked like before the earthquake. See these skids? These big skids were put in there because they knew they were at the Denali fault. And here's what it looked like afterwards. And you can see the bends are bigger because there's some compression in here and things have slid over. It was a great success. And, you know, in engineering, great success means you're skillful, but in some cases you're also lucky. So here's what it looked like when it was done. They just barely made it. And I have great respect for my Japanese colleagues who have operated the Shinkansen. Very skillful, no deaths, but also very lucky too. I mean, there have been instances, if the Shinkansen had been running during the Kobe earthquake, there would have been many fatalities. But it was early in the morning before the trains were running. So this question of how you get the pipe offset, you can do it a couple of different ways. You can put it into, here would be the fault. You can put it into kind of an S shape. Arctangent is a very common kind of shape that would be used for these systems. It's the way you'd build a freeway. The curvature increases, then decreases the other side. If you do the calculations, it's pretty simple. It's just the accelerations in here scale with the offset, and then V via the pod over the length scale of the deformation squared. So this turns out to be 1 over time, the units of this. So it's slip over time squared that gives you acceleration. And this is just the time it takes for the pod to get across this deformed region. And if you said, I'm going to allow up to 1 G in an earthquake, we're all strapped in, then the length that this would have to be with this shape to keep it at 1 G, below 1 G, would be 44 times the square root of the slip that you put in here. So if you put in 10 meter slip, you'd need about a deformation width of about 1.5 kilometers. That could be pretty expensive to engineer something to deform over such a large distance. A more efficient way to do that offset would be to put it a constant acceleration in one direction up to the fault and then just flip signs and go constant acceleration the other way. That gives you kind of a double parabola shape. Again, it's scales with slip over the time it takes to get across here, but it takes less space to get across here. In this case, your 10 meter slip with a 1 G offset would require about 700 meters of width to design this in. That would handle the shear. There's also extension and compression. You couldn't use anything like they used in the Alaskan pipeline where they put in the bends to handle the extensions and compressions. I mean, that alone would kill you even before you had an earthquake. Another issue, as I said, I'd say something like 1 in 3 significant fault offsets happen on faults that were not really recognizable prior to the occurrence, including the earthquake in Kobe, Japan. And even if you know the faults there, it's really hard to know what the maximum offset will be. If you chose 10 meters, you'll get most of them, but the maximum I've seen is 17 meters. And some people like to do statistics on these things, but probably the best way to look at this is Pacific versus North America is moving at 5 meters a century. You wait around, you're gonna have a big fault crossing event. So here's another kind of problem that shows up in this. When an earthquake wave travels through the earth, there's shearing of the earth as it goes. It's just what it's all about. And so if a wave's traveling through the earth and you're traveling through this wave field in a pod, how do things change? So this is the acceleration you would feel in a pod versus the acceleration of the ground without, if it was just sitting stationary. It's actually a pretty simple equation. It goes like this: nu squared, and then the time history of acceleration is scaled, compressed, or extended by nu t. And nu is just this factor, 1 minus the velocity of the pod divided by the apparent velocity of the wave going along the wave, this wave speed here. And this could be your friend. If you were just happened to be going in the same direction as the wave, at the wave speed, you wouldn't feel anything. I mean, because you'd just be on a stationary point in the wave and you'd just be riding it like a surfer, no problem. But of course, if you're going in the opposite direction, your teeth will be chattering because you're going to get the same displacements, but everything will just be accelerated much faster at you. If you keep following this thing, you can make it so the velocity of the pod is faster than the wave speed, in which case this factor goes negative on you, in which case you go backwards in time. Think about that you can get younger here. Not really. What it means is you're catching up to the wave field and you're overtaking it, is what that actually means. So the wave speed in, like here on the UCLA campus, the wave speed in the upper 50 meters or so is probably comparable to the speed of the pod. But it turns out that most of the waves that we'd have in an earthquake here are coming from deep, and the apparent velocities are much higher, more like 5,000 meters per second. So because those apparent wave speeds are so much higher, this is kind of a curiosity more than it is really important. Here's something that's a little more important. So suppose you've got your tube and a number of pylons that it is attached to, and the tube can swing laterally, either horizontally or vertically. Then your tube's no longer straight while you're going through it. And if you keep track of the accelerations as you go through this bent, you can do some calculations that show the acceleration in the pod. This is a spectral acceleration at the frequency of the normal vibration of this tube. This spectral acceleration divided by the acceleration that you'd feel in the tube if you weren't moving, if your velocity was zero, scales like 1 plus 3 times 10 to the minus 4 times the length squared of the distance between the pylons. So this is assuming that it's a 350 meter per second pod, and just using the diameter of the tube, you can come up with this calculation. Fairly simple, and it just says that amplification grows as the length squared of the distance between the pylons. So you want to keep your distances small. It turns out that if you take the record from this Nepal earthquake in downtown Kathmandu, and this is kind of the worst case you can think of, take a 236 meter distance between the pylons, that gives you about a 5-second natural period and it would be swaying in that record about 3 meters. And so it goes back and forth 3 meters. You're going to get through this 236 meter section is half a second. So you have to move over 3 meters and back in half a second, and the accelerations go up to 8.5 G. They're pretty high frequency because you're going through this that fast, but 8.5 G, probably that won't work. So one thing you could do is, if you knew you were about to go through a long stretch with a big deflection on it, and you had an accelerometer to keep track of the swaying of the tube, you could say, I know that tube is going to be going through, be approximately straight, say, a half a second from now or 2 seconds from now. If you're out here, you could apply the brakes, just tap them so that you hit the tube when the tube's approximately straight, and then it's okay. So you can calculate if you know when to apply the brakes, I mean, you apply them as soon as possible. Here's how strongly you'd apply the brake to make sure that you hit that thing when it's approximately straight. And it only takes a half a second to get across that section, so it all works. So here's my summary. I'd say above ground fault crossings can more or less be designed to be survivable. They'll probably be expensive, and some care has to be taken. And then there's some really curious but not especially dangerous Doppler effects that show up because the speed of the pod is so high. And it's important to keep the tube very stiff. You don't want really long spans between where you support it. And there may be some reasons to use active controls in here. Thanks.
Maybe for one question.
So how much was that deceleration, tapping the brakes, what was that acceleration value?
It's probably maybe 20% G. I haven't run through the exact numbers there. It doesn't have to be, if you've got enough time ahead of time, it doesn't have to be very much.
Right.
Yeah.
And then the second comment is the distance between the pylons being shorter makes a lot of sense. And actually, I think it's necessary for Hyperloop because it's hard to build a tube with thin walls that doesn't have a lot of flex anyhow. So they're going to have to go that direction. But of course, that makes the whole system a lot more expensive.
I think that's probably right. It turns out the bending of the tube is mainly controlled by its diameter, but not the thickness of the walls.